Welcome to this second part of the lecture on colloids, and in this part what we'll be looking at will be the electrostatics of neutral objects. Most of it will be reminders, and if some parts of it you don't know about them, then it's a good time to actually have a look. So the first question we want to address is, how does a neutral system create an electric field? Naively, we would think that if something is neutral, there is no charge and therefore there is no electric field. However, that would be a wrong conclusion. Why is it so? It's because the actual definition of a neutral system is that its total charge is zero. Okay, therefore, if you have a system that comprises n charges ranging from q1 to qn, then being neutral for that system means that the sum of these charges is equal to zero, regardless of where these charges are located. So that's what it means to be neutral, and that's all. So it means that we can't infer really anything about the electric field created unless we delve in the details of the system we are looking at. And so the simplest system I'm aware of is the system made of two charges, Q1 and Q2, and we are looking for the electric potential created by these two charges located at M1 and M2, that is far away from at a point far away from them, which is point M, located on the right hand side of the slide here. Now, you probably know that the way to calculate the potential here is nothing but the sum of two contributions. The potential created by charge Q1, okay, which will be K, where K is a constant that depends on the system of units that you are using, then divided by M1M, which is here the distance between point M1 and M. Then you add the contribution coming from the potential created by the second charge Q2, and that would be K times Q2 divided by the norm of the vector M2M. As you see, you can have the superposition principle that is directly applicable, where you add up the contribution coming from the two charges at point M. Now, in order to do the calculation that I want to do, I need to phrase slightly differently the norms M1M and M2M. To that end, what I do is that I basically put a point O, which is midpoint between M1 and M2, and I express the vector M1M as being simply M1O plus OM. Okay, so this is simply basic vector algebra, where you know that if you have an intermediate point, you can actually add up two vectors and they will give you the hypotenuse of the corresponding triangle. So you can do the same thing for the vector M2M, and that will give you that M2M is equal to M2O plus OM. Now, what I will do next is simply realize that the norm of a vector, or the square of the norm is actually equal to the scalar product of the vector with itself. And so if we do that for the vector M1M, you would have M1M scalar product with M1M will give you M1O squared plus OM squared, and then plus 2 times M1O scalar product with OM. You will get something very similar with M2M as well. Now, if you actually carry this calculation out, then you will find the following result. And this is here by using specific letters that I have put on the diagram in order to simplify as much as possible the expressions. So you find then that the norm of the vector M1M is equal to R, which is a distance between O and M, times the square root of 1 plus d over r cosine theta plus d squared divided by 4r squared. Next, you find that the norm of the vector m2m is equal to r times the square root of 1 minus d over r cosine theta plus d squared divided by 4r squared. Now, this expression has been kind of worked out a little bit in order to make only terms that are first dimensionless and that are, if not directly one, that are of the order of d divided by r. Okay, and this has been meant in such a way that we can later on, in the next slide in fact, use a Taylor expansion. So how do we do that? First of all, we need to phrase that 1 over the distance m1m is equal then to 1 over r, and then times what we had said, and here I've expressed the 1 over the square root as being simply the power minus a half. Now, most of you probably remember, and if you don't, that's not a big deal, I just tell you again, that the basic Taylor expansion to first order of 1 plus epsilon to the power alpha, okay, is equal to 1 plus alpha epsilon. Okay, here we have that alpha is equal to minus a half, and therefore you get that the expression here transforms into, or approximates into, 1 over r times 1 minus d divided by 2r cosine theta plus terms of second order. Of course, you can do the same thing for 1 over m2m. So you get, again, here this is an exact expression, and then if you use the Taylor expansion to first order of 1 plus epsilon, and then to the power alpha, which is equal to 1 plus alpha epsilon, here you would get the following result. Now, when you put all of this together into the formula for the potential, then you end up with this particular equation. Okay? This the second term on the right-hand side can actually be slightly simplified, at least in terms of notation. So if you lump together the term q2 minus q1 times d divided by 2 times cosine theta, you can actually rephrase it as being the scalar product of a new vector p with the vector r, which is here om. And p here is a quantity that we are interested in, and that is actually called the dipole moment of the charge distribution that we are interested in. So it's q1 om1 plus q2 om2. Now, once we have that, we can try to interpret a bit more what this formula is telling us, the full formula for the potential. So, if we look at the first term, we notice that it actually varies like a Coulomb term. It's 1 over r contribution to the potential. And you notice that the charge here is actually the total net charge of the system, is q1 plus q2. Okay, so you see that in general, if you have two charges far away from the system of charges, then there is a contribution that goes as a Coulomb term that simply contains the total net charge of the system. Next, the second term we have is the so-called dipole contribution. Okay, and this decays faster than the Coulomb one because the actual magnitude of this term is 1 over r squared. Okay, and of course it contains the dipole moment. Now, the reason why it's called dipole is because if you actually take a system, a particular instance where q1 is equal to minus q2, then the total net charge is 0, you've got a neutral system, and the first term actually disappears. Okay, there is no Coulomb term, if you will, or Coulomb influence or contribution to the far field due to that system. However, the dipole contribution remains as it entirely fine. Okay, and so basically if you have a dipole plus and minus, where the plus and minus charges compensate in terms of total charge, then you can still get an actual electric field or potential, electric potential due to the actual dipole. Now, the other terms that are of higher order, we won't look at them. They decay even faster than the dipole contribution, and we'll discard them for the time being. Now, once we have the electric potential, we can look at the electric field, and we will need that because, as you know, the electric field is what carries forces. You know, forces is Q times the electric field, and not the electric potential. So, to get the electric field, we remind ourselves that once you have the potential, you can get the electric field by taking minus the gradient of it. Okay, so in that case, that would be minus the gradient of K P scalar R divided by R cubed. If you want to go further, then here you can use the product rule and say that this would be equal to minus K divided by R cubed gradient of P scalar R minus K P scalar R gradient of 1 over R cubed. Now, the gradient of P scalar R is quite easy to calculate, and you can do that as an exercise. It's basically nothing but P itself, okay? Now, the gradient of 1 over R cubed, you can calculate it essentially as a gradient of 1 over, let's say, x to the n. And what you know is that basically it will make the power minus the power of the 1 over x, go basically at the numerator, and then you have to calculate the gradient of the function at the numerator. So in practice, what it gives is that it would be minus k times p divided by r cubed, then plus 3, and the 3 here was coming from the denominator of the 1 over r cubed, 3k p scalar r divided by r to the fourth, and then times the gradient of r, where r here, I remind you, is a distance, it's a scalar. You can calculate as well, this is something you've probably done in the past, the gradient of r is actually nothing but a unit vector that goes in the r direction. Basically, that's the unit vector along the OM direction. If you, of course, phrase that slightly differently, you end up with the final result that the electric field read like so. Right, this is quite a complicated expression, isn't it? So one way to actually realize what this thing is saying is basically by looking at it graphically. So here is represented in 2D, okay, so this is a 2D projection of the electric field and electric potential, in fact, of a dipole that is depicted by the arrow at the location x equals 0 and y equals 0. Now, I've depicted the arrow with a gradient of colors where the blue will represent negative charges and the red will represent positive charges. As you see, there is also a color code associated to the potential, and as you see, next to the minus charge, there is a negative potential, and next to the positive charge, there is a positive potential, as we expect. The lines that you see that are like gray thin lines that you see correspond to isopotential lines, okay? And the vectors that you see are actually electric field vector lines, okay? And as you see, they are normal to the isopotential curves. And the only thing that you need to remember is basically that they go exactly like what you imagine for a dipole. They basically go out from the north pole, if you will, or the plus of the dipole, and then they loop around in order to enter via the minus part of the dipole. Okay? Now, the very last thing we'll do will be to look at the interaction between a dipole and an external field. So if we consider a dipole that is really neutral, then we have P that is equal to Q times R2 minus R1. Okay? Now you place this in an electric field with potential V external of R, which is unaffected, if you will, by the dipole itself. Now, if you're interested in the interaction energy between this dipole and this imposed external potential, then we remember that the potential energy is nothing but the sum of the individual potential energy of Q1 and Q2 in this externally imposed potential field. So this would be Q1 V1 basically plus Q2 V2. And if you now apply the rule that, of course, Q1 is equal to minus Q2, and here I said that Q2 is equal to Q, then you get that this is equal to Q times V external at R2 minus V external at R1. Now, to move forward, what I do is simply reminding myself that a dipole can also be expressed by the position of its center. So where is the center of the dipole? And that's the point O from before, and this point will be basically called R here. So what we can do is expand basically the potential at R2 and R1 about the location R of the center of the dipole. So if you do that, this is like really basic Taylor expansion of this function, and you would get that it is equal to Q and then times R2 minus R scalar product with the gradient of the potential minus R1 minus R scalar product with the gradient of the potential as well, plus terms of a higher order in the difference between R1 and 2 minus R. And of course, if you have a dipole, then this difference will be small. As you notice, there are actually two terms here that compensate. So basically these terms compensate each other, and the only thing that remains is R2 scalar product with gradient of V minus R1 scalar product gradient of V. If you see what that means with respect to P, vector P which is equal to Q R2 minus R1, then this will give you simply that U, the potential energy of the dipole in an external field, is minus P scalar product with the electric field that is imposed from outside, at least up to first order. So we'll use this, that's the very last thing we'll do, we'll use this expression to understand how two dipoles interact with each other. So to understand this, what I do is simply to put the same picture as before with the electric field generated by the central dipole, okay? And this central dipole here will be considered fixed. Now, in this dipole, in this field generated by the central dipole, I put another dipole, okay, that is now facing downward in this picture. And as you see, on the left-hand side, I actually give you what is the potential energy of the whole system. So what you see is the bar, so thick bar in black will tell you where is the energy of the dipole, and you will see it moving as basically I change the configurations. So if we look at the configuration as it is now, you see that the dipole that I've put that is facing downward is actually going in opposite direction to the electric field generated by the central dipole. This means that the scalar product is negative, and therefore minus the scalar product of P dot E will give you something positive, and that's the reason why here you see that the thick dark bar is actually at the top and is above the U equals 0 potential value. So what it means here is that as basically this thing gets repelled, so if you get these dipoles further away from each other, the magnitude of the electric field will decrease, and therefore the potential energy will decrease and approach 0 from above. This means, as you know, that because forces are such that they want the system to go to a smaller potential energy, then this means that the interaction between two such dipoles is actually repulsive. Now, of course, the dipoles in principle can also change their orientations. And so as the dipole at the top will change its orientation, then it can actually decrease its potential energy lower than 0. So this happens as soon as the scalar product between P, the dipole moment of the top dipole, and the electric field generated by the central dipole becomes positive. Of course, if you continue to rotate this thing, this dipole, until it's fully aligned with the other dipole, then you will find basically a configuration in which the um, um, potential energy is simply minimum for in terms of orientation at least. Finally, once you are in this configuration, you see that the term P scalar E will always have the maximum value in terms of orientation. There is no way to change the orientation of the dipole in such a way that the magnitude is higher. However, what you can do is still get the dipoles closer to each other in such a way that the electric field magnitude increases. And that's what you can do. And in this case, as you see, you can lower the potential energy by actually making the dipoles getting closer to each other. And therefore, in such a configuration, the interaction between the two dipoles is attractive. Okay, so this is quite, of course, a very complicated picture, at least if you compare it to simply plus and minus charges interacting via Coulomb potential, but I hope that these cartoons were able to explain to you a little bit how these things interact with each other. And in the next lecture to come, we'll actually use this understanding, this new understanding in fact, to appreciate better how van der Waals interaction emerge in such a context when thermal fluctuations are added to the picture.